Professor, Computer Science and Engineering Department at Amrita School of Engineering, Coimbatore. And sir has publications like 9 national conferences, 12 international conferences, 14 international journals, and sir has published 2 edited book chapters. And sir has publications in 40 Scopus indexed publications. And the area of interest are video analytics, deep learning, and signal processing. Sir teaches courses in video processing, video analytics, distributed systems, and multidimensional signal processing. Sir has involved himself in developing in competency area of programming like MATLAB, Network Simulator 2, .NET, Android, Hadoop, etc. And sir has been a part of funded projects with
Thanks to the organizers to have chosen me from the institute side, and thanks to the other members who have been part of this workshop to have facilitated the things. So we will start with the session. Okay. So is my screen visible?
Yes, sir. Yes, sir.
Okay, right. So I will be talking to the people on 2 areas. One is on video analytics. Then second, I would be interested to speak to the members on knowing how transfer learning can be used for video analytics. So that's a plan of the session. I'll also demonstrate some code which I would like you to see and get a feel, okay, this is a space where I can also look at my application tomorrow and see transfer learning as a solution there. Okay. Now, for first discussion here, what is video analytics? It always says that, okay, you need to have a solution for a video, right? So a solution for a video always depends on what you want to analyze. So that's a very important thing. So you are interested in analyzing something in the video for which you would like to make a solution. When you are interested in analyzing, yes, ma'am?
Sir, we can't see your presentation screen, sir.
Oh, okay. I'll share it now also. I hope now it is visible, ma'am. Are you able to see a notepad file?
Not it, sir.
Yeah. So we are interested in developing a solution for a video, and that depends on what you really want to analyze. Now, the question somebody would ask is, what is the information that you would like to understand from the video, right? So now the information actually corresponds to asking like, what is the type of video, right? And what is the context in which the video has been taken? My PhD has been in the area of video processing, and my scholars work in video analytics, so I will try to take it as live as possible for all of our discussions. Now, the question here is like, when you say what is type of video, now here the discussion also always comes about, are you going to talk about something in MPEG video, or you are interested in looking at a video which is an AVI? Okay. Then second is, what is the context of the video? Now, for example, if you say that I have videos of faces, right? So people will start asking a question, is the video of faces that you're taking, is it actually in an e-learning classroom, right? Or is it actually in a possibility of a normal classroom? Or is it a possibility where people are there and they are actually trying to interact in the mall? So the context actually is very important. Though we talk about face detection as a common solution, we're interested in knowing the context. Is it part of an e-learning, or is it part of a classroom, or is it part of a mall, right? So this actually takes us to understand a common statement saying that, okay, given a video of e-learning classroom, right, the model is to find the faces in the video, right? So this is how you start defining a problem with respect to video analytics. Now, when somebody says video analytics, there is always a question coming up saying there's something called as image analytics. Yeah, it's also called as in the context of image analytics. So that case, what you start defining is, you start saying, okay, it's no more a video. I actually have images, right? So instead of saying video, I would say given a set of images of e-learning, right? The model is to find a set of faces in the video, right? Now, this is a generic statement because we have not started talking about what is the model that we want to do here. So this is where people always have a question. Am I going to use a model which is machine learning based, or am I going to use a model which is deep learning based? Or somebody would say, I'm interested in using a model which is a transfer learning model, right? Or somebody would say, no, it's no more a transfer learning. I would actually be interested to use a federated learning, right? So this keeps increasing, right? So the concept doesn't stop. Maybe in 2 years from now, maybe somebody would start saying there's a new model approach that is being used. Irrespective of the model that you want to choose, you should start asking a question, okay, first about what is the data that you have, right? So here in this data, you should start asking, what are the challenges in this data, right? Sometimes what happens is like the possible challenges you would get is the data is actually very less in size. The challenges you would get is the data is having a lot of noise. The challenges you would get is like the data as such does not have any label. So there's no class label to the data. These are some of the fundamental challenges. So based on these challenges, you can actually start thinking, should I go for a machine learning or a deep learning or a transfer learning or federated learning, right? So this is some of the challenges that I have come across. Once you have this found, okay, I got one challenge, right? Let's take somebody says, my challenge in the data is a noise here. Then people will say, okay, if there's a noise, use a filter, right? So nowadays we have filters which are there for image. We have filters for videos. Now in this context, people always ask a question, should I go for an image or should I go for a video? Now, when you look at the computational cost, right? When you look at a computational cost of a system, right? So that case, people will say that it's always preferable to use images, right, over video, right? But if you are asking a fundamental question, are you worried about the computational cost of the system, or you are worried about the accuracy, right? Or are you worried about the performance? Right? So here, people will say, okay, that's not a problem. You can actually go for video instead over images. So please always ask this question in your research or in your projects, right? Are you going to worry about the computational cost of the system, or are you going to worry about the performance? Now, still people will not be convinced. Why are you talking about computational cost? Why are you talking about performance? For example, if you have a camera, right, in front of your door, right, and that door can actually open once a face is authentic, right? Let's take, you call yourself as X. So if X is in front of the door should open. Okay. So here, in this case, you would still say that, yes, I want a system that will allow me to open the door when the face identifies a person as X. Now let's take, you put the same context in the situation of a different scenario, right? You are actually before a bank locker, right? Right, okay. Now your locker as such is asking a fundamental question, show your face. Now if this person is X, the locker opens. Now in this case, if you ask a question, in these two scenarios, which one is very important? Here you would say security aspect, this is very important. In this case, you would say that this is very, very important because money is there. Somebody's face, the door opens in the locker. People might take my money and leave the place. So this is what we are trying to talk about in terms of accuracy or performance. So you're not interested in compromising yourself, saying that, okay, sometime the door will open for somebody else. It's all the times it should open only for me. In that case, your system actually demands a high level of accuracy, a high level of performance. There, you need to talk about videos instead of images. Now here, the next thing to be understood here is like, when you actually talk about video, the next clarification all of us should take is like, it's not going to be just pixels, right? You are going to call itself as moving pixels. Okay, it's not pixels, it's going to be moving pixels. So if you take anything as an image, it's a pixel. If you take anything as a video, it's a moving pixels. This will take you to an understanding saying that, okay, if it is not a pixel, so what do you call it as? You call it as a motion vector. So if you have any data, let's take you have a video of e-learning classroom. Right? So if you have a classroom video, right, there you are interested in analyzing the students. Right? There the data will be processed in form of motion vectors. Motion vectors in the sense, you know what a vector is, right? It has a direction, right? Together with a value. So in video, what you can actually think of is you can represent data in form of motion vectors, and you can assume the pixels to be moving pixels. Now, once all this is done, then the next thing people should start understanding is, okay, what is my region of interest in the video? What is my region of interest in the video? For example, if you take a small scenario here, right? You assume yourself to be part of a classroom, and you are interested in analyzing what is happening in the classroom. Your region of interest would actually go around everybody's face and see whether they are happy or unhappy. Let's take, I have a video running on for each one of you. It would actually say me, okay, over the lecture for last 10 minutes, how many people are feeling happy with the session, how many people are having unhappy expressions, or some people will have neutral expressions. It's very hard to predict. Okay, so this may be one thing which I can try to find out using my region of interest. The second thing I can actually try to find out is like in my classroom video where I'm trying to address, I may try to find out whether the daylight conditions, how it is. Based on the daylight conditions, now I can actually look at an IoT based solution, and the IoT solution can actually switch on the lights in case it is very dark. It can automatically switch on the light and make the person pleasant in the classroom session. Okay, this is also possible. So a region of interest as such would actually talk about the boundary regions of the image. Boundary regions. I'm talking about regions. Reason is very simple. If there are going to be multiple people in the classroom, you're going to have a region of interest around everybody's face. So if there are 5 people, around all the 5 people's faces, you're going to have some region of interest. So you're not going to have single region, you're going to have multiple regions. Now this sets you to the next context. Okay, what can video analytics do? Okay, so now we'll rephrase the same statement which we started, right? Given a set of videos, please see the difference of e-learning classroom. So the purpose of the model is to perform the following. Okay. So what is the purpose? Let's see the purpose one by one. First one, detect human faces. Okay, and classify them as, I assume that there are 3 categories of people, right? I want to put them into 3 categories. The next is, I'm interested in evaluating the system. So I want to evaluate the system using metrics like precision, recall, accuracy, all this. So this is how you should define your statement when you're looking at a video analytics problem, right? But this you can actually extend as you want, right? You can actually start adding one more statement saying that you want to track the person, right, moving from one bench to another bench. During the class, you can see, right, one student will stand up to and will try to go and sit in another bench. So I'm interested in knowing, okay, the students who are actually moving from one bench to another bench. So the problem statement can be extended as you want, right? But most challenging here is like you have to look at the challenge first, the problem, and second you have to ask questions. Are you interested in tracking? Also, third you should start asking a question saying that what metrics you are interested in evaluating, precision, recall, accuracy. What metric you are interested in evaluating from the system, right? When you are doing something like this, what you are actually doing is video analytics. Okay, so this is what is the need for video analytics in today's research. So this is the first context which I want to set a stage for people to know, okay, what is video analytics. In a different example, if I would ask you to look at, I would I would say you like this. Suppose if you have a video of people, right? Elevators. So let's take I have a video of people in the hospital, right? Hospital. The purpose of the model is to perform the following, right? So what is the purpose would be is like first detect and track the human. Fine. This is first. Second would be is like classify person as a fall or not fall condition. Right? Somebody is walking, suddenly they fall. We call this a fall. The person is walking, the person doesn't fall. It's a not fall condition. Okay. So this is how you can actually look at video analytics. So this is the second example. First example is for a classroom. Second example is for a hospital. Any questions at this stage from the participants? Madam, am I audible?
Yes, sir.
Yeah. Any questions from the participants? Hello. Any questions from the participants? If you have questions, you can put it in the chat box also.
Sir, we have to detect the object that is human being from each image or a set of images.
Okay, fine. Okay. Okay, your question is like how to detect it as a human being, right? Okay. So I'll put the question like this. Mm. Are you able to see the notepad? Hello? Madam, are you
No,
able to see
sir.
the notepad?
No,
One
sir.
minute. I'll share it again. Yeah, 1 minute. One second. Once again, I'm sharing the screen. Tap into the screen.
observed.
Dear participants, kindly be online.
Am I audible?
Yeah, yes, sir.
Okay, thank you, thank you. The question that was asked by the audience is how to detect human or humans in the video, right? Okay. See, here what I would suggest you is like you need to first fix your region of interest first. So the region of interest is depend on the context of the video, right? For example, um, if you say that this is my boundary, okay, I'm just pulling in an example here for discussion. So if you say that this is my boundary, fixing the boundary just for reference. So in my video, I say that okay, I have pixels in the video, but my video pixel region is identified as like this. That means this is my one of the regions. Now within my video, I can actually have multiple regions, right? So within my video, I can actually have multiple regions like this. So my region can be called as region 1, and this one I can call it with respect to region 2. Okay, just for your reference, this I'm calling it as region 1, this I'm calling it as region 2, right? Now the question here is like, okay, how do you fix your region of interest? So here, if you assume that there are going to be some pixels in the moving region based on some sort of thresholding techniques, you can actually fix your region of interest. So here you can actually use a thresholding technique. Now here the next question somebody would ask is, there are going to be pixels, but some pixels belong to humans. Some pixels do not belong to humans. For example, in my video, you see my face. At the background of my face, you can see some stationary objects also. So here, what you can do is you can use a skin classifier. So that is a Bayesian skin classifier, which will actually distinguish the skin pixels versus non-skin pixels. So using that, you will be able to identify whether it's a human or not a human. Now, further, if you are interested in asking yourself, based on the human posture, right, whether the person is trying to stand and so on, I still want to see and track the humans. There is a model architecture called as postnet architecture. Using that, you'll be able to detect and track multiple humans in the video. Madam, has it answered to your question?
Sorry, yes, sir.
Okay,
But
fine.
I'm asking you, அதாவது ஒரு இமேஜ்ல இருந்து நம்ம ஒவ்வொரு இமேஜஸ்ல இருந்து நம்ம எக்ஸ்ட்ராக்ட் பண்ணணுமாங்க சார், இல்ல ஒரு ஃபர்ஸ்ட் இமேஜ்ல இருந்து அதுக்கப்புறம் 10th இமேஜ்ல இருந்து அந்த மாதிரி 20th இமேஜ்ல இருந்து அந்த மாதிரி எக்ஸ்ட்ராக்ட் பண்ணா பெஸ்டா இருக்குமாங்க?
இல்ல உங்களுக்கு எப்படி வேணும்? இப்போ ஃபார் எக்ஸாம்பிள் வந்து இப்போ நான் ஒரு வீடியோல அப்பியர் ஆகிறேன்னு வச்சுங்களேன். Let's take I'm walking in the video, right? I'm walking in every frame. Sometimes I don't walk, right? But I'm still in the frame. உங்களுக்கு எல்லா ஃப்ரேம்லயும் வேணுமா, எப்படி வேணும்?
இல்லைங்க சார், இப்போ வந்து how many persons அந்த ஒரு மாலுக்கு வர்றாங்க அப்படின்னா எத்தனை பேர் அந்த மாலுக்கு வர்றாங்கன்றத டிடெக்ட் பண்ணணும்.
Okay, that case what you can do is you can actually use YOLO architecture. YOLO architecture is there for tracking humans itself. Using YOLO architecture, you can fix a confidence value. It will draw a ROA around every human. ஒரு 10 பேர் அங்க நிக்கிறாங்கன்னா 10 பேருக்கு outerly you will get an ROI, region of interest. With that you can actually count and say that there are 10 people in the frame.
Okay, sir.
But again,
Thank
the
you.
challenge should be is like you are doing it only in the entrance of the video, correct? No, you
Yes,
are
sir.
going to do it in entrance, right? So there the context is very challenging. Only one person can come in the frame. So whenever the person comes, automatically you can run a face detection model. It can detect the face and it can detect and say one person entered, 2 person entered, and so on. Suppose if you are interested in knowing which floor is very much occupied, let's take you are a mall owner, you just want to know that there are 4 floors. Which floor is having more people? That means more attraction is there. I would actually try to take a camera footage and count the number of people there. Based on the count, I can say it's densely populated. So there is more amount of attraction for people in that particular floor. இதுல வந்து நீங்க re-identification வராது. இதுல வரும் identification மட்டும்தான். Re-identification in the sense, suppose I put my face over the frame, I go back and again I come in with my friend. I am the same person, but my friend alone is different. So there you do a re-identification there. So in this context of mall, you will not do any re-identification. You will just do only identification of people.
Okay, sir. Thank you, sir.
Yeah, thank you, ma'am. Thank you. Any other questions from the participants? Okay, the more and more you start looking in the context of the problem, you get more and more challenges. Like Madam's question should have got you an idea. Okay, there's something called as identification. There is something called as re-identification of people in the video itself. Now, the first part is done. That is, what is video analytics should be clear for people. Now we will move on to the second part, which is transfer learning. I'm picking this presentation URL because this is very standard. And in quick time, you will also understand what is transfer learning, right? See, what is transfer learning is you are interested in transferring the knowledge of one model to perform a new task, right? It's called as transfer learning. It's in a way, you're calling it as something called as domain adaptation. For example, let's take, you take a small example for understanding things, right? So, for example, I have got a robo, right? That robo can actually detect colors. Fine, okay. Now, that robo as such, once it is able to detect colors, then it can take an environment. And in the environment, it can learn something. So, what is this environment? Let's take this environment is having a lot of fruits. So, it can, using the colors, right? You can try to find out, okay, there is an apple, there is an orange, right? There is a papaya. So the context is there's a robo. The robo as such can actually use the colors. Using the colors, it is able to learn it's an apple, orange, or whether it's a papaya. Okay, right? Now, when it is trying to use colors, it will also use some characteristics like shape also. Based on the shape of the fruit, it can distinguish between orange and some other fruit in the fruit category, right? Now, you have got a model here. So let's call the model as X1, fine. Now what I want is, I want to use this model X1, right? And I want to use it for another application. Let's take the other application I'm interested in using is, I'm interested in finding out what are the objects, right? What are the objects in the scene? Now, interestingly, the objects in the scene has got fruits, got chairs, has got tables, right? Okay, and it has also got some objects related to some sort of cosmetic items. Now, what I can do is I may try to use this model X1, right, with some extra learning. Please understand the concept. Because if you take any object, including chairs, tables, cosmetic items, it also has colors. It also has some shape. But I need something more, right? For example, a chair would have an orientation. A table would actually say that it is also having an orientation in front of itself to the user. A cosmetic item will say that it is also having some stones and so on. So I might use this model X plus some amount of extra learning. I can learn the objects in the scene. This is where people started looking at something called as transfer learning, right? So if there was no transfer learning, now the question comes like this: there's no transfer learning at all. What would have happened? People would have taken all these objects again, right? And they would have started doing the training again from scratch. That means there is no model X1. Please understand the concept. There is no model X1. If the objects in the scene is having fruits, chairs, tables, cosmetic items, what the model would have tried to do is the model would have tried to do a training. Again, the model would have tried to do the testing followed by that. But this is computationally costlier because there is already a pre-existing model that has already learned the fruits. So since the fruits characteristics, especially the color, shape, has got some similarity to the objects in the scene, why not use that same model with some amount of learning and try to create the model which can actually recognize the objects in the scene? That is where people started looking at something called as transfer learning. Okay, that is why we say that we are trying to do a domain adaptation. So this is domain 1. What is this domain 1? It's got domain with respect to fruits. We're trying to use this domain and learn the objects in the scene, right? This is what is called as transfer learning. Okay, so the same thing you can see here, transferring the knowledge of one model to perform a new task. In a way, we are trying to do something called as domain adaptation. Why are we doing this? As I told you, you need not train the model again from scratch, right? You can use a pre-existing model and you can make that model to adapt to the given context of the problem. In a way, you are trying to create a cheaper model, and it will also be intelligent because it is learning from a pre-existing model. So it will be calling itself as a faster model also, right? Next in discussion is the difference between traditional learning and transfer learning. Now, when you look at traditional learning, what happens is there are many tasks that is in front of you, right? Each task is part of a learning system. So when you are trying to do a traditional learning, what you do is you take every individual task, right, and run it as part of a system in parallel. But when you're going for transfer learning, what you're doing is you're having some tasks that you've already run. What is the task here in this example? You've already created a model to learn the fruits. So the model is available. The model is called as model underscore X1. Now you are interested in using that model knowledge as part of a learning system to check input data. What is the input data that you have? The input data is basically the objects in the scene, right? Input data is the objects in the scene. So given the objects in the scene, whatever model that you created with respect to fruits categorization, you're trying to find the objects. So this is called as transfer learning, right? So transfer learning differs from traditional learning because a transfer learning imbibes the knowledge that it has learned from the previous input data and uses that knowledge as part of categorizing or doing some prediction with a given target data. In transfer learning, there are different categories. It calls itself under three categories. One is called as inductive transfer learning, transductive transfer learning, and third is called as unsupervised transfer learning. Inductive, transductive, and next is called as unsupervised transfer learning. One example of inductive transfer learning is classification and regression. Transductive transfer learning is classification, regression. Example of unsupervised transfer learning is clustering and dimensionality reduction. Example of dimensionality reduction is PCA, principal component analysis, and other example of uh, dimensionality reduction which you can call would be is LDA algorithm, that is linear discriminant analysis algorithms. Right. Now, what is inductive transfer learning is you are trying to adapt an existing supervised transfer learning model onto a new labeled data set. In transductive transfer learning, you are trying to adapt an existing supervised training model on a new unlabeled data set. Okay. And in unsupervised transfer learning, you are trying to adapt an existing unsupervised transfer learning model on a new unlabeled data set. What is this labeled data set? What is this unlabeled data set? If people are having clarifications here. A small example which I would put to people is, let's take you go back to 2019, right? Let's take you say April 2019, right? If you had got an image, somebody is asking you to find out, okay, that person has a fever called as COVID, right? Then you would say, actually saying, I do not know what is COVID, right? As a layman's I'm saying, right? So there is no knowledge or there is no class label called as COVID at all. Now let's talk about now, September 2022, and there's an image and somebody says, okay, classify the person as COVID. You would say that, yes, I have training data already with a class called as COVID, right? Doctors have already told all these images are called as COVID images. So you would say there is a training data with class called as COVID, right? So I will be able to classify the data. So in this case, the challenge here is the model that you will use is the model will be an unsupervised model. Reason is there is no class label, right? I'm just setting a few things for everybody's understanding. Don't mistake my discussion as very basic one. So here it says that I do not have any images with respect to COVID. So I need to go for an unsupervised model, and it means that there is no class label at all. So here it's not like that. I can actually go for a supervised model because there is already a class label. There's already a training data. The training data says very clearly that it is actually falling as COVID or not COVID. So that is what we are talking about here in this context of inductive, saying adapt existing supervised training model on a new label data set. Transective, adapt existing supervised training model on a new unlabeled data set. Unsupervised, adapt existing unsupervised training model on a new unlabeled data set. So transfer learning has got different applications. So one is image classification. Just now we were saying, no, if I have a set of images belonging to fruits, I have created a model for it. Can I actually use that same model and learn what are all the furnitures in my room? So that's an example here. So next one is text sentiment classification. So if I have a set of text, can I actually classify the sentiments as positive, negative, neutral sentiments? Then similarly, text translation to new languages. You know very well that letters across languages are similar. Suppose I know to learn what is the letters in Tamil. Can I use it to learn something from Malayalam, right? So like this, transfer learning has got multiple applications. So in transfer learning, it's something like this. You are trying to create your own AI model because it falls under unsupervised category. So here, when you talk about the neural network layers, right, I think in context, each one of you know what a neural network is. So it starts classifying, saying that you need to create a model to learn a given input data. And once you have created a model using a given input data, it can be generalized for any type of test data. Okay. One second, I'll switch on my battery. Okay, so clear. So transfer learning has got multiple applications, as I told you. You can take it for application where you have a data and you can learn something from the data and use it for some other input data being provided. So here in transfer learning, we can actually assume that there are layers and every layers will have possible way of capabilities. Now, when you look at layers, you should understand that there is layers at the bottom, there are layers at the top. So you can have general level of learning at the bottommost layers. For example, if you have an input image, you can assume that you can learn the edges, you can learn the shapes in the input image under the bottom layers. As you go up in the layers, you can start learning other features from that given image. Features can be eyes, feathers. If you look at eyes, each portion of the eye has got a set of edges. So this is small example that is presented here. This is for a VGG net architecture. So here, if you can see here, under the first set of convolution layer, this is examples of filters. Now convolution layer 2, example of filters. Same under convolution layer 3, example of filters. Now, as you go down, what you should understand that you can see that there can be complex shapes. You can see here there can be complex shapes rather than talking as just pixels in the first layer. That's what I was saying you, as you go higher in the layers, you can increase the learning complexity of the features, what you want to learn from the given image. So in transfer learning, what happens is you are trying to give an input data and you will try to have the model created. So this model can call, assuming that it is able to do a task called as task A, right? Now you will try to transfer that knowledge for a new input data B, right? Assume the input data to be B. So whatever you would like to see in common between A and B can be taken and you can learn the model, right? So when you're doing it every time, you are trying to say that whatever you learn from A, you're able to adaptively learn it for task B also. And in the process, it might work or it might not work, right? Because the learning is always not steady. For example, you take up an exam for mathematics. For the first time, you get 83 marks. You expected 90 marks. That means your expectation is I expected 90, but I got only 83. So there the answer would be like I have to go back and start learning again and again. That means you are trying to fine tune your learning capabilities. This process here in neural network would call itself as a back propagation. So in the process of back propagation, you will try to readjust the weights in the model and learn again. So this would take you through a fine tuning process. Now, once you are doing this, then it means that you have done 4 steps here. First step is you have created a model, and that model you call it as a pre-trained model. The next what you are doing is you are trying to partition your network into 2 categories called as featureizers and next is called as classifiers. Now what is this featureizers and what is this classifiers is? As part of transfer learning, you would say that some set of layers will take care of extracting the features at every stage, right? So that will be taken care by the featureizers. And at every stage, there is possibility for the layers to replace. So this is called as classifiers, right? Where will you go for replacement test? It is like this. Suppose this is a model that I have created for learning the fruits in the given scene. I take that same model and I'm trying to apply it to a model of finding the objects in the scene. What happens is some layers that is already there is fixed, right? That is featureized, and some layers will involve some changes because it cannot be directly adapted to finding the objects in the scene. So that is where you see this next step here saying classifiers, which says which are the layers to replace. Now once you've done it, you will retain the classifiers again with the new set of data that you have. The new set of data in this case is example of furnitures, chairs, tables, or objects in the scene. This process keeps going and again until your model is giving a higher level of accuracy, right? So when you say you're doing a freezing and you're doing a fine tuning, it is like this here. If you see here, you have convolution blocks, right? So you can see here convolution block 1, 2, 3, 4. All of the convolution blocks will have two operations. One is convolution and next is called as max pooling. These two operations are same set of operations that you see in a normal deep learning model. The next step, what happens is it fine tunes the convolution block. In the next case, here the block number is called as 5 because this is block 1, 2, 3, 4, block 5. So here it fine tunes a block 5, right? And then what we can do is we can try to again fine tune our own fully connected classifier. So the classifier will have general operations, which is a normal flatten operation, which is there in deep learning, and a dense operation, which is part of deep learning. So when you're doing this, you can see here that you are coming across two keywords. One is freezing and fine tuning. So freezing is happening in block 1, 2, 3, 4. And when you come to fine tuning is happening in block 5, right? So this keeps again and again going until it is able to generalize for a new type of data given in the model. Now the next question somebody would ask is, which layer should I retrain, right? There's no answer for it. Reason is like, you can actually depend on the domain of the problem. Based on the domain of the problem, you can select which layers you want to retrain again and again, right? Or other way of answering the same question would be like you retrain the model again and again until you are able to get a higher level of accuracy in the model, right? Then the next question somebody would ask is, when should I go for fine tuning? So if you have a model A and it is trained on a data set called as A, now question is, how do we apply the transfer learning which you have done with model A to be applied to a model called as B, right? That means you have checked with dataset A. I would like to check it with the dataset B. Don't get complicated with the discussions. It's same thing what we are talking about. Dataset A in the previous example that we were talking about is fruits. Dataset B that we were talking about in the previous example is actually objects in the scene. So whatever we have learned from A, that is fruits, I'm interested in adapting to the objects in the scene. So how do I do it? So how will I go for a fine-tuning process? So here, there are generally 4 categories here. One is, you take the dataset similarity, right? If the dataset similarity is different in model B, right? That means dataset B has a very different dataset similarity compared to A, right? You can train the model B from scratch, but you will take the weights alone from model A. So the weight initialization procedure alone will be taken from model A in case your dataset B is very large and it is different from dataset A, right? Now, second case is dataset B is similar, right? But it is larger in size. It is similar to dataset A, but it is larger in size. So here what you can do is, you can actually do a fine tuning, right? And you can check whether the model works correctly. The third category is the dataset B is very much different from dataset A and it is smaller in size. What you can assume is that you can train the classifier using the earlier layers, right? Earlier layers in the sense you can actually take the layers which we have frozen. Please understand the concept. You can take the dataset and train with the layers which is already frozen, right, at the bottom level layers, and then you can recheck how the model works. That is for the third category. Fourth category is dataset B is exactly similar to dataset A, but see the change. It is not larger size. The dataset B is smaller in size. So here we will not do any fine tuning, right? Because it will result in overfitting. So we will just train just by using a linear classifier. Okay, so this is how you can actually look at applying a given data set which is provided with a transfer learning approach when you have a pre-trained model for an existing data set which is called as A here. Only constraint you should look at here is how much the data set is similar. As you can see, similar, very different, right? That means very different means it's not similar. Second thing you have to see is the data set that you have taken, that is data set B, right? In this case, whether it is smaller in size or whether it is larger in size. Once you have decided it, you can use any one of the recommendations from the given table. So next one here is, what about the learning rates, right? As far as learning rate is concerned, you can actually use a general learning rate that you set for the model under transfer learning, but fine tuning as such can happen over a period of time. This process is not simpler because you need to go forward and you need to modify the weights again and again in the model. Now, to get a closer insight into what we are trying to talk about here, we'll just take this UI for discussion. I think this people know, playground.tensorflow.org. Now, whatever you have with yourself to experiment, you are calling it yourself as data. Now, the data can have any type of association like this. You look at this, it's very hard to classify. You look at this, it's easy to classify. You look at this, you will say that it is very easy to classify. You look at this last one, you will say it's very tough to classify. So this is one of the challenges why techniques like transfer learning has come in. People initially had linear classifiers wherein they used to say that we can approximate the problem with a kernel, right? With a kernel, I can actually try to classify the data into one or more classes. But as the data became very challenging like this, people felt it is very hard to use a linear kernel. So there, the solution was to go for a non-linear kernel. So the challenge was like we can go for a non-linear kernel. With a non-linear kernel, we can approximate the data and we can learn the data as quickly as possible and say that it is falling into a respective class, right? So the next challenge here is the training versus testing. Suppose I'm going for a data set which is having a training label already provided. Usual process would be like associate 70% for training and 30% for testing, right? Noise is inherent. If you're working on images, compulsorily you will have noise. So whether you will actually use a pre-processing technique to remove noise or not is in the challenge of the problem. For example, let's take a face detection video and it is taken in a very clean sunlight. There's no need for a noise at all. Suppose you take a face detection video which is of a driver who is driving the car and outside the car there's a lot of rain. So the question here is like, how will you detect the face clearly when the rain is a noise? Please understand the concept. Here the rain itself is a noise because the rain will impose a lot of pixel values which will superimpose on the face and it will say that it is not a skin pixel region belonging to a face at all. So there in such cases you need some sort of filters. So there are a lot of filters that has come, and most common filter that is used in video processing is a Gaussian filter. So the Gaussian filter is taken as a very common filter with respect to video processing. So you can use a Gaussian filter to handle the noise. So if you are looking at filters also is a good thought process in developing the model. Now, the next thing that you should know is in all deep learning architectures, right, including transfer learning, there is something called as hyperparameters. There are something called as parameters. Hyperparameters means what you fix. In this discussion, we have been saying again and again something called as learning rate. So what is the learning rate you would like to fix is a hyperparameter. What type of activation function you would like to fix is an hyperparameter. There are different activation functions. The most common activation function in models related to deep learning and transfer learning is ReLU, right? ReLU is a very nice activation function which people can use. Next is regularization. What type of regularization you would like to have? L1, L2. The next is what type of regularization ratio you would like to fix. All this that you're providing, right? That means you're manually setting is an example of hyperparameter. What you're calculating is actually a parameter. So test loss is a parameter. Training loss is a parameter, right? And next is the layer level details are also examples of hyperparameters. We have been saying again and again that we have some convolution layer. Then people say, okay, can you increase your layers, right? In deep learning here, you can actually increase the layers. And interesting thing is, it differs from neural network saying that for every layer, you can fix your number of neurons. Please see the change. At every layer, you can fix your number of neurons. It need not be same. As you can see the stacked architecture, no? From one layer to another layer, the number of neurons is varying, right? This is a next difference in terms of deep learning architectures. Now, given this set of hyperparameters, example, the layer details, learning rate, activation function, regularization rate, we are interested in running the model. When I say running the model, it means that you're going for a forward propagation. That means it learns from here to here, right? And every layer is connected by weights, right? Every layer is being connected with another layer by weights. So when you are doing a execution of the model, it runs forward, it runs backward to calculate a parameter called as loss, right? So one forward, one backward propagation together is called as an epoch. Please understand, one forward, one backward propagation is called as an epoch that you can see from here, right? Now, once you go and click this, it means now the forward, backward, right? And it gives you something called as loss. So this model can run for an infinite amount of time to make sure that the loss is minimal. Once you say that the loss is minimal, that means the model that you created is the best model. So you can use that model with another type of data that you create, right? So this is just a dashboard display. It is built on the internet. This is just for you to quickly understand what happens in the process of model execution in terms of deep learning, right? Now, the next question somebody would be interested to ask always would be like, what about the software environments that I should use when I'm trying to use any sort of models like this? So here, the software environment preferably could be Python. And since you are talking about learning architectures, so your learning architectures that you're trying to create can be done by using PyTorch, right? So you can do it using TensorFlow. Okay, this is also possible. Okay. The next is to make things better. In terms of hardware, you can actually have a GPU to make it faster, or you can try running the code in Google Colab, right? Because Google Colab is one other environment where people are now comfortable to run the code, and Google Colab also has a premium license for all your information, right? So since you get a premium license, it is like you get most of the facilities as if you are running your code physically in the server, right? Server of Google itself. So in Google Colab, you can execute your code. It's a Google Colab environment. So here you can go and push your code and you can run. You can run the code free of cost, but in case if your code is having a lot of requirement to use massive computational resources, you can run it under a premium license also. That is also possible, right? Okay. Now, this is the first set of things which I want people to know in the discussion. I was very interested to talk to you about video analytics, transfer learning, how transfer learning differs from conventional learning, and next, a quick summary of parameters about how transfer learning can be applied, right? In case you have a model. That means what is hyperparameters, what are parameters, right? What are the general settings that you can do in the model, what is forward propagation, what is backward propagation. Okay. Now, next to understand would be like, what are the different transfer learning architectures? Okay. So when you say deep learning, people will say there's something called a CNN, right? So similarly, when you go to internet and type different transfer learning architectures, you'll get a lot of architectures, like UNet is there, right? ResNet is there. So there are many different transfer learning architectures being available. So VGG is there, right? So this is one good URL which I show to people because it gives you a quick summary of how to compare the different transfer learning architectures. Because when you do your project or research, your question would be like, I'm using transfer learning. I'm interested in comparing the transfer learning architectures also. So in this analytics, indiaimag.com, you can actually see the good explanation about the 4 transfer learning models they have compared. Right. So here they have looked at inception net, exception net, VGG, and next is ResNet. Okay. So just see here, we've already learned what is transfer learning, all that. So here they have taken an ImageNet dataset. ImageNet dataset is let's close this. Yeah, ImageNet is a predefined dataset available. So here there are many images. So what they have tried first is like using inception net. Using inception net, they have tried to take the given data, and when you go to inception net, you can actually try to have the architecture defined over the layers. So here, if you can see here, the type of activation function that has been used is rectified linear activation, right? And dropout percentage, they have set to 70% is a dropout. And they have tried to use a classifier where there is a linear layer with a softmax loss as a classifier. With this, they have run first type of model in transfer learning. Second one is exception model, right? So this exception architecture as such is one of the architecture that is developed by the Keras library developers itself. So here, this generally has 3 type of flows. One as an entry level flow, then middle flow, and next is an exit flow. So here they have run the model with the same ImageNet architecture, and they have checked. Third is a VGG architecture, which stands for Visual Geometric Group Architecture. So here they have tried to take the architecture and run it against ImageNet dataset. Okay, this is a layer architecture details for VGGNet. So last that they have taken is ResNet architecture. So ResNet architecture is being checked against the ImageNet architecture dataset. So this is a layer level details, and they have tried to see the results. Now see the comparisons, right? This is what I want people to see here. Now how they are presenting the comparisons is, first is in terms of number of parameters for each of this architecture, right? Okay. Next is the complexity level of each of the architecture. So this is low, low, high, and this is low. How they are given it as high is based on the number of parameters. If you can see here, for VGG, the number of parameters is 113 million, whereas all the other 3, it is 23 to 22 millions, that's all. So it's all low, this is classified as high. Speed as such, since the number of parameters is less, speed will be high with respect to inception, exception, and next is ResNet. I'm again repeating, since the number of parameters is low for inception, exception, and ResNet compared to VGG, it is assumed to have a speed of high, whereas VGG will have a low speed, right? Okay. The next, what is the unique feature for each of these architectures is, in inception, it is generally said in theory itself that the large filters will be replaced with small filters. When you come to exception, your depth-wise convolution will be followed by a point-wise convolution. And VGG uses small number of kernels, ResNet will use mapping based on skipping the connections. So these are all general unique features for all these 4 architectures. The second level of comparison is presented based on the accuracy. See here, when you come to architectures based on deep learning, transfer learning and all, you will come across something called as a top X accuracy. What is this top X accuracy is? See, when you take models with respect to machine learning, what it will say is, okay, let's take, I have classes of data, right? So the classes of data that which it is with trained in this rabbit, or let's take it as snake. So I have a model which is pre-trained for classifying rabbit, tiger, and next is snake. Okay. Now, when you're going for a ML model, fine. So what it will say is, it will take for every sample, sample 1, sample 2, okay, sample 3. Please understand the concepts. So this is test data. This is a test data. With sample 1, it will try to say whether it is tiger. Fine. So it says this is snake. This is actually rabbit. Please listen, all the participants. I know it is taking time. Please listen. It will be understandable for you. Now assume that this sample 1 is originally a snake. Okay. And the sample 2 is originally a snake. Right? And the sample 3 is originally a rabbit. Right? So please understand the concept. The sample 1 image that is originally taken is actually snake, but it is classified as tiger. Sample 2 is a snake, which is classified as snake. Sample 3 is a rabbit, which is classified as rabbit. Now in this case, what happens is your accuracy would be saying it as 2 by 3 because 2 samples have been correctly classified, as you can see here, no? Out of 3. This is what actually happens in your ML. So if you put your accuracy, it is 2 by 3. Now when you're going for a transfer learning model or a deep learning model, like deep learning or transfer learning model, you talk about something called as top X accuracy. So this will be slightly different. What does it say is, it says for every sample, right, that you take, let's take, you say sample 1, right? It would predict as tiger at the first score. In the next score, it would like to say it may be a snake. In the next score, it will try to say it will be a rabbit, right? Okay. So this gives you an advantage because rather than saying that it didn't correctly predict a snake in the first case, here using a top X accuracy, you'll be able to try to come to some sort of justification saying that the model is able to predict it as a snake in the second level of confidence. Okay. So this is a metric that you're calling it as top X accuracy here. The same metric is what you can see it under this case. Now you take all these 4 architectures, inception, exception, VGG, ResNet. You can see that the top 1 accuracy versus top 5 accuracy. Top 5 in the sense, it means that the entire model has been classified with 5 type of classes. Okay, the entire model has been classified with 5 type of classes. The top 1 accuracy, it says 0.782, 0.941 in terms of inception. But see this exception, it is 0.790 and top 5 accuracy is also high. So in conclusion, what is being presented here is exception architecture is having higher value with respect to top 1 accuracy and top 5 accuracy. Right? Okay. So this is how you can actually compare the architectures. Now the summary of discussion here is to make you understand, in case you want to use a transfer learning model, you can always use transfer learning architectures like VGG, inception, exception, ResNet, fine, and you can compare them from 2 perspectives. One in terms of the model characteristics, the other which you can look in is in terms of the accuracy parameters, right? Now with all this being seen, now the next which we'll have to take it for discussion is about the codes part, right? So we will see some sample codes that we have made. Once again, I'll share this code screen. Meanwhile, is there any questions from the participants? You can clarify. Any questions from the participant side? If you have any questions, you can raise the questions in the chat box also.
Participants, any queries?